I'll say something really in-depth, like a man who needs no introduction.
Classica.
Hi, everybody. Roland here. Thanks for tuning in. And I'd like to welcome you to the June PARSEC meeting. Back from for a second engagement is Dr. Terry Bridges with the RECON concept of citizen science, photometry-based citizen science. Dr. Bridges comes to us from the Okanagan Valley. In fact, he's a professor at the Okanagan College. And it looks like he's got a co-author that he's stealing images from. But I'll let him introduce his co-author.
Thank you very much, Roland. And I want to make sure, how do I tell if we're actually recording here or not?
Oh, are you?
I thought I was. Oh, there. I'm just going to, yeah, it's recording. Okay, great. Whoops, let's go back a second. Back. Okay, yes. Okay, so thank you, Roland. It's great to be here at Wilson Coulee. My first time here. I also got to see the Rothney Observatory on Wednesday, courtesy of Phil Angel, who's also here. Yeah, so this is my kind of, about a year ago, I did give you folks a presentation on RECON. So some of it will be, if you were at that talk, you'll have seen before, but I've added some new stuff. So hopefully you'll find something that's of interest to you. Yeah, so there's a lot of people involved here, but I'd say the main person is JJ Cavallars, who's at Herzberg Institute in Victoria. He's actually a planetary astronomer, unlike me. I'm more of a galaxy person, so I'm still a novice at this solar system stuff. So, and yeah, I think I did hear a little ding there. Okay, so I'm going to tell you about this RECON project and some of the things that have come out of it. So this is kind of an outline. So I'll just talk a little bit about TNOs, or Trans Neptunian Objects, and why they're important and interesting, how we use the technique of stellar occultations to measure their sizes. I'll talk about the RECON, which is the original US project, and then CanCon. So RECON stands for Research Education Collaborative Occultation Network, and CanCon is the Canadian extension of that. And I'll talk about that. Talk about our first result a few years ago, the Goblin, and then some other results that we've got in the year since. And then I think the stuff that's new since I talked last, sort of New Horizons and how occultations is featured there, the spacecraft that went to Pluto and MU-69, and the Lucy mission, which is new, visiting Trojan asteroids, launched last year, and how RECON fits into that, and then a little bit about the future, which is always a little murky, but there we go. Okay. So TNOs, Trans Neptunian Objects. So here's kind of a, hopefully you can see my cursor okay. So we're looking, in fact, on the y-axis, it's a bit funny. It's actually, it's inclination. So the sort of the tilt of the orbit relative to the Earth's orbital plane. And we're going out in distance here. So here's Saturn, Uranus, Neptune, and Pluto is here. And so we're considering mostly here, we're looking at objects beyond the orbit of Neptune, the TNOs. So all these objects going out here, out to fairly large distances here, out to about 80 or 90 AU, astronomical units. So these are the things we're talking about. So this is a little movie, courtesy of Alex Parker, which plots the discovery from the early 90s of TNOs over time. You can see how they really, several thousand now. So I guess the field's about 30 years old in that sense, in terms of observation discoveries. And yeah, over time, so we're up to 2012. More searches are ongoing. The groups that are using the Cannes-Francis Wide Telescope to find more of these responsive searches. Rotating and on. I didn't think we're going to 2030, so I'm not sure what the deal is there. But anyway, it gives you a sense of how big the field has become. And but yeah, you should go to his website. He's got lots of nice visualizations like this. Oops, let's not play it again. So this in terms of the types of TNOs. I'm not going to spend too much time on this. But if you're really interested, there's a great review article by Brett Gladman, who's at UBC. And I'm not sure Volk's last name, but this is in the annual reviews of astronomy and astrophysics last year. So it's a good review. These are figures stolen from that. So there's various types of, various types of TNOs. The blue ones here are called the resonant TNOs. And those are ones that are in resonance with Neptune. So 1-to-1 would be objects that are co-rotating with Neptune. 2-to-1 would include, for instance, objects. So 2-to-1 means that for every 2 orbits of Neptune, this object does 1 orbit. So they're integer, right? So there's obviously a connection with Neptune. Neptune is keeping them in these special orbits. And 3-to-2 is Pluto and the Plutinos. And you probably know for every 3 orbits of Neptune, Pluto does 2 orbits. So we've got a lot of these objects in these resonances, but we also have other types. There's so-called detached ones, the yellow ones that are basically not interacting with Neptune, and they're kind of found all over the place out here. And then we finally have the scattering ones that are interacting, kind of being scattered by Neptune into sometimes quite large orbits. And then we have the classical, which kind of between 40 to 50 AU or so, which are, again, not really, they're not really interacting at all. So there's different categories, which we don't really need to know the details about, but in terms of their sizes and some of the known TNOs, which of course includes Pluto, whether you call it planet or dwarf planet. Anyway, it certainly, I think it fits as a trans Neptunian object, so let's call it that. And of course, it's got lots of moons, as you can see here. And the sizes here, this scale bar down here is 2,000 kilometers, right? So Pluto's just under about 1,800 kilometers, I think. And so the biggest ones, and it's, we've detected ones down to say 100 kilometers, or even with a technical talk about occultations, down to 10, 20, 30 kilometers. So you can appreciate these are still not big objects, and they're far out. So it's hard to study them from the ground and to determine their sizes. So why are they important? Well, they're interesting because they're in the outer solar system. So they tell us a lot about how the solar system formed and how it's evolved. And so if we can, for instance, if we can find objects that are pretty primordial, they'll represent material that really came from the original formation of the solar system. And the distribution of TNOs, the ones with different classifications, tell us a lot about how the solar system formed, about the migration of the outer planets, and how TNOs were carried along with that and scattered by the giant planets like Neptune. So it's kind of a cold component that probably formed at large distance and basically stayed there, survived. But this sort of hot component formed at large distances and was sort of scattered out by interacting with giant planets. So to better understand TNOs and how they fit into the history of the solar system, we'd like to know a lot more about them, like how big they are. If we know their sizes, then of course, we can measure their masses, perhaps from their moons. We can get their densities. That's really nice to know. Are they, how dense are they? Are they rocky? Things like the Earth, like Pluto. Their composition, what are they made of? Their total numbers. I mean, how important are they in terms of the mass of the solar system? And their dynamics, their orbits and such, which again tell us something about how they've interacted. So lots we would like to know, but it's hard because they're small and they're far out, so it's difficult. But we can learn something by looking at the colors of these objects. So here I'm plotting a V minus R color on the y-axis, so red things at the top, blue things down here, and on the x-axis is another color, B minus V. So again, blue going to red here. So you can see they span a whole range of colors. So the color tells you something about the composition, of course, surface composition. Spectroscopy, if you can get spectroscopy of these objects, I'll tell you more. But there's a lot we don't know about the composition of these objects. So learning their sizes and maybe densities will help with that. And so here's, for objects that we do know their sizes, we can get good estimate of their albedos, how much light they're reflecting, how shiny they are. And there's a range, right? Some like Quar, quite dark, other ones like Pluto, Makemake, Eris are fairly shiny, fairly reflective, so fairly high albedo. The thing is, we really need to know the sizes before we can determine the albedos. We can measure how much light one of these is reflecting. We know its distance, but we need to know its size to know how much it is reflecting or its albedo. So just keeping an eye on the chat. Okay, so yeah, so Michael's out, yeah, B minus V. Yeah, so it's definitely a color. Okay, so let me talk now about this occultation method. How do we determine the sizes of TNOs? And it is one of the few ways, besides spinning a spacecraft like New Horizons with the Pluto and MU-69, it's really hard. Like I said, they're pretty small. We're talking maybe a few hundred kilometers out at, 40, 30, 40, 50 AU. So it looks like points in a ground-based telescope. So, but the occultation method is a brilliant method for determining sizes, although it's not as simple as you might think. So the idea is that you've got a background star here, and you've got some object in between in our solar system. Here it says asteroid, but think here, in my context, I'm thinking of TNOs, but it applies equally well to asteroids. And the idea is if you can predict when this object is going to block out the light from a background star, and you put a telescope there, the star shadow is going to fall on your telescope. And if you measure the brightness of the star before, during, and after the occultation, you can determine if there was an occultation. And in particular, you want to measure the duration of the occultation because that will give you a handle on the size. Obviously, a bigger object is going to block the light for a longer period of time. So knowing how quickly the shadow is sweeping across the Earth and the duration of the occultation, that gives us the size. Now, if you only have one measurement, you don't know whether the star went across the middle of the object or across the side. So we call those chords. So with one detection, you get a handle on the size, but you don't. Ideally, you like to have multiple detections, and I'll talk about what that looks like. So that's the technique. So it's a pretty simple, geometric technique. Here's it kind of in practice, you might say. So this kind of illustrates what you're looking for here. And if I can play this movie here, there we go. So there's telescope. So this is in 2015, the TNO, and you'll see in a second, you'll see the star is going to be occulted. It's between the two red lines. So look carefully there, and in a little while you'll see that star disappear. Right there, disappears for a few seconds, and then look, it'll come back eventually. Yeah, I'm not sure. I guess it's kind of slowed down a bit too. So now it's come back, right? I think that was maybe something like 15 seconds. I'm not exactly sure. But that's, so when you do these things live, you're kind of looking, you're looking on your monitor to see if you can see it, but they're pretty faint. So usually you have to look, you have to look a bit later. I want to go back and just show, no. So this is again, the light curve, right? Before, during, and after. And the flux of the star pretty much goes to zero here because it's completely blocked out by the object. So that's the technique. So they tell us lots. So we can measure the size from occultations. And, and if we do have an estimate of the mass, maybe from some assumptions about what the material is, or if it has a moon, we can use Kepler's laws to give the mass, and then we get the density. That tells us, obviously, that's pretty important quantity to know about what it's made of. And we'd like to know kind of what is the distribution sizes. Are there a lot of small objects or some big, what's the kind of distribution? And that tells you about how these things formed, right? It tells you about the early stages of solar system formation. And if we combine the sizes and the shapes with brightnesses, how bright are they? We know their distances. We get the albedo, how much light they're reflecting. And if you can get spectra of these objects, spectroscopy, you can learn even more about the composition of the surface. Also, if you can detect these objects in the infrared, maybe with the infrared telescopes, space telescopes, you can also learn something about the temperatures and how quickly they're spinning. And of course, if you have really good data, you might be able to detect in the atmosphere. I don't know if this will ever happen, but it's possible. But certainly you could hope to detect rings and moons, right? It's kind of secondary occultations. And of course, when you observe an occultation, you get a very precise position for the TNO. You know exactly where that star is, well, within, say 10 milliarc seconds. So you then have a good orbit point. And that's really important for refining the orbit. So that's another piece. So lots of useful information, but there's also lots of challenges, right? So the idea is that for the RECON project, there's a group, Mark Buey and his group in Colorado are basically taking star positions now using the Gaia catalog. So we have a good, relatively good positions of stars. So we need to know star positions and of course the orbits of the TNOs to predict when there's going to be an occultation. And the problem is that, even the star positions could be better, and they will get better over time. We also need to know the orbits quite well, and that's kind of the limiting factor because we often have only observed, a fraction of the orbit. So as time goes on, this will get better as well. So things will improve. The durations are quite small, for the smallest ones, maybe a few seconds. So you've got to make sure that everything works and you catch it. So 5 to 50 seconds for sizes of say 100 to 1,000 kilometers. So you need good time resolution, right? You want to take lots of measurements so you get maybe ideally several points in your occultation so you can really define that duration well. And you need to have, the problem is that even with our best star positions and orbits, the predicted location of the shadow path on the Earth is actually quite uncertain, up to several hundred kilometers. So that means that you really can't afford to just put one telescope out and hope to see it. You need a whole network. The longer the better, and the spacing will determine what kind of size resolution you can determine. Obviously, the smaller the spacing, and if you have a detection with a few stations but not others, that will really help to refine the size. So you need to have trained observers along the predicted shadow path, big enough telescopes, but 14, 16-inch telescope is fine. Bigger is better, of course. You can look at fainter stars. You hope to have good weather, and you need precise timing. So it's sort of the trade-off between all these, right? How many events you can predict depends on your equipment and how many people you have in your network and such. So there's certainly challenges to be overcome. Okay. So let me tell you about the specific application of this technique, the RECON project. And so it started off as a US NSF funded project. And again, Mark Buey at Southwestern Research Institute and John Keller, University of Colorado, are the sort of two PIs here. That's sort of the two folks who lead the project. Mark is a very busy guy. He's involved, you'll see, in space missions like Lucy. So he's doing a ton of ground-based support programs. I don't know how he does it all. So originally funded through the National Science Foundation. And they have just under 55 telescopes along the kind of the west coast of the States. Been going since about fall 2014. It's kind of a mix of amateur astronomers and high school teachers and students that man these sites. The telescopes, and I'll talk more about our setup, as a good digital camera, and you need also the precise timing. And of course, if you extend the network, maybe up into the north in Canada, you get even more chance of observing these events. So JJ Cavallars and I, a few years ago, were thinking this would be a great project to bring into Canada. So we now have sites in the Okanagan. So there's one down here, which is Anarchist Mountain. Probably folks have heard of Peter and Deborah Saravolo. That's their site, an amazing place they have. You'll see a picture of it. High school in Oliver, another high school teacher, Bruce Gow, who actually he and the students built their own observatory a few years ago. Dave Gamble and Mark Force, who are RSC folks in the Okanagan. We have a high school site in Kelowna, and we just recently moved last year, a site in high school in Vernon to Thompson River in Kamloops. And we've now added the Calgary RSC, and I know you folks are still working on the camera, getting that working, but hopefully we'll get that sorted out and you'll be another site. We also have Sleaford Observatory in Saskatchewan as another new site. We also have, yeah, and also Victoria with JJ in the high school. So we've added about 10 sites in Canada. So we extended the, the length of the fence, we call it, by about 15% or so. So that, that helps. And we've actually made some detections as well. Okay. Anyway, those I've just said what those groups are. So I won't go through this again. It's a mix of RAC and high school folks. This is the Saskatchewan site. This is Gerald Jansen, who's actually on the Skynet network, one of their telescopes. And so we're just getting that commissioned as well. And this is Sam Lawler, University of China, and some of our baby goats. You can never have too many baby goats, I think. So I'm not going through all this, but basically we kind of started mid-2017 planning things. We got our first equipment in the spring of 2018. We've added sites since then. We had a team meeting at Anarchist Mountain, which is wonderful. Saskatchewan and now Calgary in 2022. So we're continuing to grow. So here's our team meeting. So yeah, the Saravollos have this amazing site. This is one of their domes. They have more than one. So basically, they're the Cadillac operation here. They go into their dome, they take a glass of wine, they sit down, they punch in the star's position, and everything's set up. They don't have to freeze their butts off in the cold like the rest of us do. So here, let's see, this is actually, that's JJ Cavallars there talking about TNOs. That's John Keller, one of the US folks that came up. That's one of our Skywatcher telescopes that we, most of our groups have. And I'll talk more about those in a second. So here's our, so most of us have these, but some of the RC folks have their own telescopes, and but most of the school sites have these Skywatcher 14-inch Dobbs. And these work pretty well. They're a bit heavy, but the two sections detach, and we've had pretty good success with those. And we have a CMOS imaging camera, a QHY device, which has, the CMOS devices are great because they have really fast readouts. They're quite, they're quite sensitive, and it has a built-in GPS and timer. So we get, on each frame, we get the timestamp and the position. So that's really what we need for these events. Skywatchers are about, well, they used to be about 50, about 3,000. I'm getting mixed up. The camera, one of them is about 1,500. I think the camera is about 1,500. And I think the telescope's about 3,000, at least a couple of years ago. So, one of the great things about this kind of observing is you don't need a big telescope. You don't need a 30-meter telescope. We can do it with, smaller telescopes, which is, I think, really great. Okay, so this is kind of the things that we've done. We've done probably approaching 30 events since October 2018. We have typically several teachers and students coming. And I forgot to mention, one of the great things about the project is that if you take part in an event, even if your site does not detect, occultation, but other sites do, and there's a paper, everyone gets their name on it. So including the teachers, the students, and the RSC folks. So it's a really great citizen science project. So we've actually, our group on our own has had, participating with the whole network, has had 2 detections and papers out in progress. People are enthusiastic. Sometimes 3 o'clock in the morning is a little tough, but and I think it's a nice partnership between RSC, between NRC with JJ, myself at the college, and the US people. And again, the citizen science project aspect of it. And this is a quote from one of our teachers. Yeah, students kind of like this. They also, I think they like, especially the social aspect, just getting out, in the middle of the night. And but they're also, okay, so I want to tell you now about the time here. Okay, about some of our results. What have we found? Well, this is our first sort of the CanCon detection. This is done with a Penticton group, high school. And this is one of the most distant objects in the solar system. So it's about 80 AU at present, but it goes out to about 2,300 AU, 32,000 year period, and it's on a very eccentric orbit. So it's a really distant object. This, by the way, is a little quick, you blink and you miss it, just sort of the discovery of this object. You can see in the middle there, that object is moving relative to the background stars. And that's how, of course, we find these things, right? We take images of the sky and we look for things that move relative to the stars. And so if there was a prediction in October 2018 that there would be shadow across the Okanagan. And so Bruce and the students, some of them there, observed it. Yeah, he has an amazing group of students. So here's a little movie showing you, there's the star that's going to be occulted. This is kind of a loop that, but you can see it's there and it's not. And so they detected an occultation, which is fantastic because they're the only group to do so. So, oops. If I can go to the next slide. So there's basically so this object, I'm going to mispronounce this, but Lelea Kona. Here's the light curve. So here's a couple of standard stars that didn't get occulted in the frame, and here's the actual star that got occulted. So they had 2 data points in the occultation here, and here's a fit to it, the red kind of square fit. From that, measured, determine the duration of the occultation, and knowing the speed of the shadow path, found a radius of about 110 kilometers, so about 100 kilometers or so. And albedo, 0.21, which is sort of typical for objects at that distance. This one's about 8-second duration, right? So you've got to be all ready to go, and you observe for 15 minutes before and after, and hopefully you actually catch it. And they did. And so here's where it kind of fits in here. So this is basically albedo, reflectivity, shiny things at the top, dark things at the bottom, versus size, and it fits in kind of nicely with other objects we know at those distances.
For me, RECON was an amazing experience. I got to experience the pressure of pressed for time in those scenarios when we were recording. We had to get all our tech problems sorted out while we were all in that confined space. We had to work together really well. Another thing that was an amazing experience from RECON was being able to mention it on university applications. You can get questions asking for extracurricular activities or some like super cool experiences you've had. And I mentioned RECON.
Yeah, I guess
you can really go on forever about this kind of stuff, but I'm going into engineering, and being able to be part of a research team before university is a big advantage when you're going into university, and it worked out for me.
It's kind of nice to see the impact on the students too. So all 3 of those students have gone to university, and I think they had a really good experience with RECON. So I'll just tell you about some other, I'm going to just see, okay, there's nothing to chat. Okay, so just tell you about some other results, not necessarily from the Canadian part of the network, but just from the whole RECON project. So here's a couple that were observed in one in January 2019, other September. Here's the location, sort of the central, shadow path. But here's the dashed red lines are I think the 1 sigma uncertainty. So the uncertainties are quite large, right? That's why, again, you need the whole network to have a hope of catching these things. And so here's the sites. So actually, Sarah Voldos and Anarchist Mountain actually did take part and observe this event. And here's the groups that actually, the 2 red ones down here in Nevada that actually detected the occultation. But the important thing is that a lot of other sites took place, and if they don't see detection, that obviously that really helps to constrain the size. So even if you don't see it, it's super important that you took part. Here's the other event later in 2019, and here's 3 sites this time detected. So that was quite nice, a little further south. So here's for the first one, here's the 2 sites that detected, only 1 point here, maybe 1.5 points here. So you'd like to have more points, but these are fast, and sometimes the weather isn't good and you need to increase your integration time. Lots of constraints going on. And Carson City down here. I think this is really I'm not sure, not really some issues here, not a detection. So here's sort of the size. So it's about so this is measured to be about 16 kilometers. So you can measure pretty small objects at these really large distances. So that's the power of the technique. And a fairly low albedo, and the other one later in 2019 with the 3 detections and a bit better, 2 or 3 points. So better constraints. Yeah, still, yeah. So fairly small and certainly, but a bit bigger, 65 kilometers and a lower albedo. So, so these are kind of two of our detections. Nice to see. That was written up in 2021, Planetary Science Journal. This one was fun because I never expected we'd see this. So this involved a binary TNO, so primary and secondary. And so you can see the secondary object and the primary TNO, and the binary star occultation. So, so secondary. So this is for the primary star, and this is for the secondary star. These two, and you see slightly, different sites. You can see again the red are the detections and so on. And so here's, yeah, I won't go through all this, but here, this is the secondary star, and this would be the primary object, the larger of the TNOs binary system, and the smaller one, and again for the primary star. And you can see some cases we have multiple detections here. You can see these multiple lines intersecting, so we get a pretty good handle on the size. Only one here, so it varies, right? But we did have detections of basically all configurations, and you can kind of see them up here. And from all that, so
this thought to be a binary object in the solar system prior to this occultation, or was it discovered to be such?
it was, yeah, it wasn't known. You're right. It wasn't known to be. I'm pretty sure it was not known to be a binary TNO before this. Because I think actually, let me look. So the the angular separation between the primary and secondary is like 16 milliarc seconds. So that would be pretty hard to do from the ground at least. So I'm pretty sure this was discovered to be a binary. So that was pretty cool. And so this is the most favorable model statistically speaking. So I wouldn't say it's 100%, but that's our best interpretation. That and again, albedos and things. So that was kind of a cool discovery. Okay.
Also, you don't know if they're like a true binary or just two objects that are far apart in space, but along the same cross section across the sky. Yeah?
The star or the TNO?
The TNO.
Yeah, the TNO. Well, yeah, I suppose it's possible that they're not, physically associated, but I think, I don't have a good answer to that, but I think it would be, I would imagine it's unlikely that they would be a chance, but I guess you couldn't rule it out probably. Yeah.
The whole thing is unlikely. So.
Yeah. Yeah.
It's cool.
This object, 2002 MS4, one of, in fact, the largest unnamed object in the solar system, as far as I know, or TNO in the solar system. This is from another group, did a huge campaign, and they have like tens of detections, right? Different sites detecting it. So here, with this kind of data, you can actually not just get the size, but the shape. And if you kind of plot the residuals, do a best fit of all the data and plot the residuals versus angle, you can see there's some places where there's dips and maybe some higher. So maybe interpretations that we're actually seeing some surface features, right? Something like 20-kilometer-ish mountains or depressions. So when you get this kind of data, you can actually say a lot more about what these objects look like. So actually, this object was also observed from by the Cerevolos in Arcus Mountain, 3 separate times. So we have 3 different events here, and of course, each time, the duration can be different because you may be going through the middle of the star, or the star may be going through the middle of the object or off to one edge. So you don't expect them to be the same each time. But basically, this was written up by a student working with J.J. Cavallars from Concordia University, and so we just published that this year. So kind of corroborating the size that these other folks found. Something like, yeah, my zoom window is, sorry, how do I get rid of that? I guess I can. So about 750 kilometers. So it's a big object. Yeah. Oh yeah, hide video panel. Oh no, actually, no, I didn't want to hide the video panel. Maybe. Show video. No, I want.
Hide the floating meeting controls. Yeah, that's it.
That's it. Thanks.
And then
Thank you. Okay, so now this, I want to kind of talk about some kind of the tie-in of ground-based projects like occultation studies with space missions. So the first one is the New Horizons mission, which visited Pluto, and then, so Pluto was 2005, was it? Have I got that right?
15.
Or 15, sorry, I knew it was a 5. 15, and then about 4 years later, went past another object, MU69, now called MU69. And of course, if you can learn something about the object before you send the spacecraft there, that's really useful. So Mark Buey did a bunch of ground-based programs in this is in South America and also in Africa to try and measure, get an occultation measurement, maybe learn something about the size, learn if there's maybe another moon or something that you might, like to know about. So the spacecraft, so you could try and avoid it. And so they actually had good success in July 2017. So these are basically, this is kind of the yellow points are really kind of showing you the shape. This is where the star was occulted. And so it is a strange shape. And so some possible interpretation, maybe it's a binary system, that from one vantage point looks like it's a contact binary, but it's actually not. Or it could be a true contact binary, or it could be a weird potato shape. This is from James Tuttle. And so here's when they actually got the first data from New Horizons. There's JJ there looking pretty excited, the team. There's Alan Stern and the PI. So it is a contact binary. Here's sort of one of the best images, Erikoff. So the basically kind of confirming the occultation study. So maybe we don't need some spacecraft. No, I'm just kidding. We want to send spacecraft. Okay, the last piece I want to talk about is the Lucy mission, which is even newer. And I'll talk about one of the objects, Euripides, that Lucy will look at. But let me play you a little movie here. That's by the way, that's Mark Buey. I stole this, I captured this from a presentation he gave with his permission. So here's the Lucy mission that launched last year. And it's doing a very complicated fly past, but it's looking at the Jupiter Trojan asteroids. So this leading group here, and it's going to actually see 4 of as the object kind of swing past it. Then Lucy visits an object in that's the weird part, yeah. I know, I wonder that too. And then it's going to look at one object in the trailing Trojan. So, oops. I'm just going to play that one more time because I like it. So again, the Lucy folks are really interested to know what can we learn about these objects before the spacecraft gets there. So Mark has been doing a whole bunch of ground-based missions. He was just, I think, in Australia last week or a couple of weeks ago. But I'm going to show you just some of the results from a successful occultation detection of Euripides, one of these 4 objects in this group here. Okay. So this is a little bit about, I guess, the Lucy mission, right? So these are the objects that it's going to be looking at. Here's the 4 there. Euripides, one of the bigger ones, and then there's some smaller ones. And then binary, Patroclus, and Minucius. Here's a spacecraft. This is, I guess, what it looks like. So it looks like there's a hint, right, that Euripides actually has a moon or some kind of companion. And there's lifting off. And this is a sort of ground-based picture, I think, of the system here. So these together will be one of the last object that Lucy will measure. So here's from October 2020. I was hoping to go down. This is actually done in Las Vegas, but I was too worried about COVID, and but it would have been cool. But they had some nice results here, right? Lots of detections. There's something like 10 stations here that detected it. And again, we're kind of seeing, so there's no evidence of another binary, another companion from these data, but there's some hints maybe, right, from the deviations from this best fit, that maybe we're seeing some, again, surface features here, right, of Euripides. So again, with multiple detections, you can try and say something about the shape and maybe surface geometry. Best estimate of the size is like 72 by 59 kilometers. And so Mark is basically trying to repeat this with as many of those other objects as possible before the spacecraft gets there. So he's keeping pretty busy. Okay, so yeah, so I'll kind of leave here. I'll say, I think the future is good because we'll get better predictions of the occultations with better star positions and better orbits. Now, things like the Vera Rubin Observatory and the LSST, Legacy Survey of Space and Time, Vera Rubin is going to map the whole sky repeatedly, right? It's looking for transient objects. So it's going to find lots of things like supernovae, but it's going to find a ton of more TNOs. Maybe it's probably going to increase by a factor of 10, the number we know now. So we're going to have a flood of TNOs, and again, we will need to follow this up, right, with things like occultation programs. We hope to extend the CanCon network. It'd be nice to go further north if possible, but also it's useful to extend it further east. The more stations involved, the better. Yeah, I'd like to get participants more, like especially the schools, this more involved in kind of the whole data analysis. So we're thinking about that. At the moment, each group sends their data into Colorado and it gets reduced. So it'd be nice if we have some ways that we could make that a little more interactive. Yeah, Mark and John are really interested in trying to get funding for a robotic network that would kind of supplement the people-based network we have. So you could have a bunch of robotic stations that could observe any possible, could be low success rate, but you got these robotic telescopes, use them. So we could, again, keep the ground-based, or keep the, the people involved for higher probability ones. And so we'd have kind of two networks. There's also, we wrote a proposal, and it's a proposal to study more binary systems in the Jupiter Trojan asteroids, kind of a test of how we think these, Trojans were transported into those regions. Haven't heard yet. And we're actually still waiting to hear whether RECON will get funded, continued funding in the US. So there's some uncertainty, but hopefully it will continue, because I think hopefully it's seen as important. And I'll just leave there my email and the website if you want to check anything out. And I'd be very happy to answer questions. So I'm gonna, because I hid, how do I get back?
Escape.
Escape. Right, okay, so I'll keep an eye, okay, so I think they're, so maybe we'll just, I guess, can you guys, I can't, I don't know if I can, it doesn't make it any bigger, does it? Okay, so let's look at it. Okay, okay, good. So Michael's asking, is web going to get into this, do you think? That's a good question. My guess is that, I don't know. No, in fact, sorry. I know that web will be involved. In fact, there's Wes Fraser, who's an astronomer at the Herzberg Institute, has got web time to image TNOs. I don't think web will be involved in the occultation part of it in any way, but certainly web will be great to try and image these things. It's hard from the ground, and web will be amazing for that, I think. So web, yeah, so web will have a role to play in looking at TNOs. I mean, I think the perception is right that web will be looking at the very early universe, young stars and the first stars and galaxies, but it's also going to be doing a lot of solar system stuff. So that's a good question. Peter's has to be a lot of uncertainty or variance in these measurements and differences between the observing information from these different sites. That's true, yeah. And it is a challenge because sometimes not every site has the right, we want to have the right files, like the camera files to tell us, what the settings were in the camera, and the GPS files. So sometimes they don't always happen, or we have files in the wrong format. So it's a challenge for sure. And it's kind of an ongoing headache for Mark, who tries to put everything together in the US. So we're thinking about ways we could improve that. Yeah, Mike, I love that animation that I stole from Mark. What is the real minimum a telescope would be? I'm sorry, I guess I'm not sure what that question means.
How small a telescope would be usable in this project?
Oh, okay. I would say, well, at the present time, when we don't have a ton of objects, I would say you probably want at least a 12-inch telescope. With the 14-inch skywatchers, we can do occultations maybe to 16th magnitude, because we want to have, it depends on how big the object is, because it would, you want to have a certain number of data points to measure an occultation, and bigger the telescope, the shorter the exposure you can use. So I would say with Vera Rubin, we're going to get a lot more, but I would say probably at least, you want 14 or 16 inches even better. So I would say 14-inch might be a, but I should see folks here actually in the room have questions too.
So it's really a function of the brightness of the star. That's your limiting determination of the aperture of the telescope, right?
Yeah, it is. And of course, the weather isn't always good. And if you have a bit of cloud, then you have to integrate longer, which means that, but you can't go slower than a certain time, or otherwise you're going to miss the occultation. So yeah, so the brightness of the star is really the, limiting thing, for sure. So Michael asked, so the high school groups have the 14-inch skywatchers, and of course the nice thing is they can use them for other things too, not just RECON program. So they can take them out. QHY camera is great. You can obviously see it if you have a nice monitor. You can get a lot of students looking at it.
So those telescopes are on a driven Dobsonian mount. Is that how they're tracking?
It's basically a go-to telescope. Yeah.
Yeah. So it's doing. Obviously, we're looking at fairly short intervals of time that we're. Otherwise, a field rotation would be an issue. But
yeah, you're right. Yeah, typically we're. Yeah. The event itself is short. We observe for maybe 10-15 minutes on either side. So yeah, so that's not really a factor. One thing we want to do is probably it can be hard to, one of the challenges is actually finding the right star. Some of these fields are really crowded. So we were thinking of maybe putting focal reducers on, so we could actually get a wider field and make it a bit easier. But with practice, the more you do it, better it gets.
If you're lucky enough to have the time to image the field beforehand, and get familiar with the star field and compare it to Sinbad or something like that, it helps a lot.
Yeah, actually, you're right for sure. So what I do is I send out, like RECON produces like star maps, obviously, and I go also, with say DSS image. Yeah, so in some cases, like people like the Cerebolas, it's easy. They will observe it beforehand and make sure they can identify it. The high school group's a little harder because, so we don't do that, but that would be good. That would be good practice to do that all the time. Yes, for sure. Oh, sorry. Someone's saying can't hear the question. I'm sorry. I apologize. I meant to repeat the question. So there's been questions about, I guess, the logistics of it, of the observing. Phil was asking, what is kind of saying that the star brightness limits, is it kind of the big limit? And I said, yes, that's definitely the case. Sorry, what would
field rotation?
Yeah, Phil. Yeah, sorry. Roland was asking, is field rotation a problem? And it isn't for for our relatively short exposures. Yeah, and I mentioned we'd like to the challenge is finding the field, so the focal reducer. Yes, I'm sorry. I apologize for that. Okay, other questions?
Peter's got one on the screen there. Is it possible to show your initial slides again? I guess maybe some people got caught off by our email. Maybe
The bait and switch.
the bait and switch, yeah.
Yeah, you know what, I mean, one thing I could do is, although they're a bit big with the movies and stuff, the files are a bit big, but I could put my slides on like Google Doc or something, and I'd be happy if people wanted to download them. But
Of course,
So-
we have a recording.
We do have a.
oh, and of course, yes, we are recording this too. Yes, yes, of course. So yeah, so this is recorded. So yeah, that's the best solution. Though I'm also happy to show my slides. Peter, were there? I know how many. I guess you don't know how many slides you missed, but I could go back and show the first 2 or 3 if you like.
I was also back at the beginning, some of the things, slides, conjured up some questions, but I can't remember them now.
Okay.
So,
Let me try and go back. Oops,
oh,
I seem to have. Whoa, hung my. Oh. Wow. Okay. Yeah, the
There, Peter,
slides.
have you seen them all?
Yeah, so my first few slides are just sort of talking about the what we're talking about, and we're particularly looking at objects beyond the orbit of Neptune, trans Neptunian objects. So I didn't mention, actually, this is the kind of the classical Kuiper belt, right? The blue objects here out to 40, 50 AU.
there's a legend on the lower left, the H parameter, what is that about?
Oh, actually, oh yeah, what is it? It is some estimate of the magnitude of these things, but it's, oh, I forget. It's not like a
The
conventional
standard, like
magnitude.
absolute
It has to do, involves the albedo and some assumption about the albedo and the size. Yeah, I can't remember how it's defined. Yeah, it's kind of a weird magnitude-ish thing. So I talked about, yeah, we're looking at anywhere from, from Neptune up, right? Here's Pluto, and then the Kuiper belt, and then some even more distant objects. I'll just play this ball. This is the history of the discovery.
What's the doc?
I guess there's that Neptune. I'm not sure what. Oh, I can't see the internet. I'm thinking it's probably Neptune. Yeah. Okay. So, but yeah, it's not quite on the. So I guess it's one of the probably one of the first objects. So I don't know. And then we rotate it to the side. It's always fun to do. Well, there's a lot of these things, and like I said, Vera Rubin been increased by a factor of 10 at least. But anyway, yeah. So Peter, there's a recording that these folks will post as well. I'll have to send you the link to it. Yeah. Let me put the chat back up here. Yeah. Do we have other questions?
So the data goes to Colorado, is that right? And they, these are FITS images that you take?
Yeah, so Phil saying the data goes to Colorado, yes. And they're FITS images. And most of the time they're FITS. Sometimes people forget, but
What about filterless, is it preferred?
filterless, yeah, we're just interested in getting as much light as possible. So yeah, so we don't use filters. Yeah, the data gets sent to, uploaded to Colorado. Mark Buey sort of processes them and basically runs. So there is some software that any group could use. And I blank on the name now. Oh my God, sort of coming from the asteroid community, or from the variable star group.
Those guys?
Yeah, absolutely. Yeah. I'm blank on. I'm so terrible with names, but there is some software that we have used, and you can basically take your frames, right, load them in, and you plot the brightness. You basically compare the brightness of the star in question with a few stars around it. So you're basically doing difference photometry. And then you can see if you have a detection. I think Mark does something a little fancier. And so basically looks through all the different sites and was there a detection in any of the sites. And then basically you fit a model to each site that has a detection, get the duration. And if you have multiple, then and again, I'd like to know more about what Mark actually does at this point. I think his photometry is actually a little more sophisticated. He's doing kind of PSF fitting photometry, where you fit the point spread function of the stars. But I don't know. I'd like to know more about. But Mark's so busy that it's hard. It's hard to find out. Yeah. So there's a lot of stuff going on that it'd be nice to know more about. And could we have each site do more of that? I think it'd be more interesting. Yeah.
And the distances to these things, is that still measuring a number of points and trying to compute the orbit?
Yeah. Yeah, and if you have a good enough orbit, then basically Kepler's third law, right, to get the distance. But some of these orbits are not that well known. Especially the newer ones where you might only have a small fraction of the orbit. So that's going to improve over time when basically follow up these objects and improve their orbits. But some are better than others. Yeah.
But I think they need at least 3 points to one guess. And more to get a better angle on it.
Right. And what are they using for? Is there a website you go to for predictions? Like in your area, for blah blah blah.
Oh yeah. Okay. Well, actually, let me. So Phil was asking, how are the predictions for occultations made? So actually, I'm just going to go to the RECON. I'm glad if I can escape from this. So where is the RECON? I had it loaded up here. There it is. Yeah. So here's the RECON website, and so there will be observation campaigns, for instance, and so there's basically these are basically automated. We take basically the Gaia's star catalog, all the known TNOs, and predict when there'll be occultation. So again, I don't know much more than that but there's basically a kind of a list produced. But you can see that the probability here at the end is the probability that that one site might detect an occultation if the whole network activates. And so obviously we only activate if it's say about 30% or so. So
did you set this up that you were in Huntington to get this calculation list? I mean,
this is okay. So this is basically, this is not site dependent. This stuff, it's basically the positions, the date, predicted. Oh, sorry, the times. Yeah, are probably. Yeah, actually, that's a good question. It would be. For one site, I don't know, probably one of the US sites, I don't know.
Okay.
Yeah.
It says it's a global candidate list though, so I don't think it
could be actually for the core of the Earth.
Right.
Yeah. But for an event that, let me show you. Okay, so that's one. And then there's a better selection of those that will have more chance of being observed, right? So this one, say hopefully August 17th, this is when we might observe because it has a chance of almost 50% of being detected. And if you click on, then you can see, so here's the location. Oh, okay, the shadow path. Here's kind of a star hopping. Here's a map. And so here's for our sites, right? Here's the first one is the Canadian sites and then the US sites. And you can see the track, the predicted location. So this one would be nice for more of a chance of a southern US site detecting it. This site is right on the predicted, but the uncertainty is quite large. So that's why we.
So sorry, what is that parameter?
This is the distance of that site from the predicted center of the shadow path.
Okay.
Yeah.
Yeah.
So this would not be a great event for the, but it's so important that everyone goes up, but we wouldn't expect to detect anything in the north. Yeah, so once, so for a given event, yeah, then there's the predicted times for each site.
You're not sharing your screen, apparently.
Oh, shoot. Oh, there's too much. Sorry, folks, sorry. Okay.
Go back to the front page.
Yeah, so let me go back quickly to, so this is the first page I showed, which is, well, actually, it wasn't the first page. Well, this will be fine. So this page is a list of the higher chances of success ones. Here's the probability I was mentioning. And this one, we looked at the one in August 17th. Has almost 50% chance of being detected. So these are the ones that are most likely. That
There's an 80% one total.
and that is actually amazing. Why?
Lower. Two green ones.
So this one surely must be. So here, now of course it also gives you the magnitude of the star. This is a pretty bright one actually, 12.7. So this would be easily seen with our, in good weather. So there's the star, predicted stars, nice star field. And here's, so again, here's the times, and here's the distance from the center of the shadow.
Susanville.
Susanville.
That's where you want to be.
Yeah.
Gimple.
So-
Gimble's too far.
So that's amazing that it's such a high probability.
If you click that link, does it give you the more detailed map?
The RECON map link.
Oh, actually,
There's one that sometimes gives you the, like the center line and the chances. are-
yeah, you're right.
Or did you just download the PDF?
Oh, sorry, it's downloads the PDF file, in which I should have shared my whole screen. Okay, so let me just share my whole screen now so you see everything. Desktop. Okay, so here, yeah, here's okay, yeah, so here's a bit, yeah.
That's the best.
So that's the kind of,
Predicted.
but then the uncertainty's probably off, either not shown or
Well, that's a
Track
really-
limit.
that's a
So-
Or
really
two,
well known- it's a really well known.
that one, yeah, actually
Yeah.
this, yeah. So this must be, this, yeah, this obviously has probably previous detections, which we had a really precise determination of the orbit. So,
Right.
yeah,
But it could have a companion.
exactly.
we
So
should go after it.
absolutely. So, yeah, I don't know if we have gone after previous detections or not. So that might be a first. Yeah, so that's some of the tools
So
you get.
how frequently were the predictions? But it's like once a month, couple of months? Like-
Well, it really varied, but
Yeah.
yeah, typically, yeah, I mean, maybe a few a semester, so maybe one a month-ish,
Right.
but they can come in clumps too. Like we had,
Sure.
maybe we had like 3 in 1 month or something. And then you can, a couple months go by. So it's a bit random, but yeah, a few a semester. I guess, we also don't want to overload folks with,
Must be the usual problem too. In the summer, you're looking more to,
yeah.
you got more stars, but you don't get the dark.
Right. And then-
Can you please back that up to include Western Canada? Okay, I'm not sure what, okay, anyway, what else?
Yeah, what did you mean, TM? Back it up, just zoom up or something?
Yeah, I'm not sure what he means there. So there's this, so there's, and then there's sort of previous campaigns, and yeah, you can see what we've observed or tried to detect before. Mix of objects. There's also there's a bunch of resources about how to use equipment, publications here, so you want to check out what's been published so far. So, well, the map of the, okay, yeah. Sorry, Michael, I may have gone. I'm not sure which page we're looking at, but
You did find that one map with the track that we could see.
Yeah.
Sure.
Yeah, I'll pick a different one. And we'll get better.
There, maybe that's the ones.
yeah. that maybe the one that you're looking at? Okay, I can try and something like that maybe. But that is kind of an untypical one.
You want the screenshot, so just scroll down a little bit so you can see the path a little better. Not the screen, you know, screen. Carson City, you know.
I don't know. Yeah.
Okay, you got it.
Okay, great. Super.
Cool.
Yeah.
Cool. What is